All right, last one today. So let's finish up what we started last week, which was ray tracing. So just a quick recap. We introduced ray tracing, the basic principle of it, and we talked about the framework that we need for that, how we can represent the windows, the pixels on the screen where we want to shoot our rays through. Then we talked about how we can create those rays and how we can calculate then intersections between the rays and objects. Most of it was just repetition of stuff that we have done before, because we talked about intersections before, of course, but were some new things like the representation with a matrix in matrix and linear equation system form for the triangles, for example. I also mentioned only quickly the shading, because we again did this before. And then we talked a little bit about more advanced shading techniques in ray tracing, shadow feelers, ideal specular reflection, and refraction. These are like really extensions that make some really nice realistic effects. But the interesting thing was, of course, also that they fitted very naturally into this general framework, because, for example, when we calculate when we implemented the ray tracing, how we can shoot and trace rays towards an object, we can also use that implementation to implement, for example, shadow feelers, which is nothing else than just taking a ray at a different position, shooting it towards the light, and then see if we hit an object or if we hit the light source, and that way know if we have to draw that point in shadow or in light. Good, so we saw these extensions, and now today we want to go more into these advanced techniques, and one of them, the next two of them, are more not related to shading, but more related to the actual geometry of objects that we have. So in this course we're not covering modeling, but we talked a little bit about very basic geometric shapes, for example, spheres, triangles, and so on. But even like small extensions of this we didn't cover. Like, for example, we know how to model a sphere, but we don't know how to describe an ellipse, for example. And no, we didn't explicitly learn how to describe an ellipse, but we actually know a way how to do that, because an ellipse, if you think about it, or if you look at it, you see, well, if you look at a nicer drawing of it, you see that an ellipse is nothing else than a circle that is transformed with a non-uniform transformation and with a rotation. So the non-uniform transformation makes the circle wider and pushes it a little on the top, so we get an ellipse, and then we do a rotation, and then we get an ellipse like this. So yeah, we can, or this is that example is it is a non-uniform scaling, then it is a rotation, and we can move it. And this way we can easily create more complex objects. And there is a technique called instancing, which is often used in ray tracing, which is basically we take one standard object and then we use transformation matrices to create so-called instances of that object, which are basically slightly transformed variants of that object. So for example, here we create, where's my pointer here? Here we have a circle, which is one of the really basic objects that we had. And then we transform this and create an ellipse, which is just a non-uniform scaling of the circle. And if we want to have this flying saucer, we also have to move it down a little, so it's scaling and translation. And then we can use that as an object. It's just called O here, just to represent the object or all points that are associated with it. And then we can apply transformation matrices to it. So for example, here we have scaling and translation. And here we also have scaling and translation, but we also have rotation. So we see here how we can easily create more complex objects based on these very simple basic objects. And that helps us, of course, in the creation of these objects, but it also, if we do that in our modeling, we can save some storage with this, because we can just store, instead of storing all those objects explicitly, we can just store the basic object that we use for the creation and store the transformation matrices that we use to create them. And depending on how we model that and what we want to do, for example, if we have a whole fleet of these flying saucers, we can actually save also some storage with that. But of course, the interesting question is now, if we want to do ray tracing, how do we calculate the intersection of, for example, a randomly rotated ellipse with array? Because we know that for how we do that with a circle, but for an ellipse this is of course more complicated. Now that is actually the major advantage of this so-called instancing technique, that this calculation is actually quite easy, or can be done in a very easy and straightforward way. And the trick is that, or the key characteristic that we are taking advantage of here, is that intersection points are preserved under the basic transformations. So if we have an intersection point here and we do the transformation here, of course we have different intersection points here because we have a different object, but they are relatively seen at the same positions at the object. So if we calculate these intersection points and then do the transformation, we will end up getting the correct intersection points here. So let's look at this in detail to see why this works, or how this works. Oh, sorry, I forgot to update the image. So that is not R, we call the array P of T. And this is also P of T. So what we have here, let's look at an even simpler example. Just look at a circle. We have an original object, which is a circle, and then we apply a transformation matrix M to it to get, for example, this rotated ellipse. And now we want to do ray tracing, so we have a ray that we shoot here. Oops. So we shoot here as a straight line. Yeah, that looks, no, it doesn't look better. Anyway, it's supposed to be a straight line. And now we want to have those two intersection points, let's call them P1 and P2, for the ray P of T. So we want to calculate these two intersection points, but because intersection is preserved under the basic transformations, instead of calculating these, we could also just apply the inverse transformation to the ray. Then we get a ray that probably looks like this. That's nicer. So this is a ray, let's call it P dash, which is the transformed version of this one. So P dash is M, the inverse of M times the vector, the ray P of T. And then, let's write it down. And then we can calculate here the intersection points, which are then, let's call them P1 dash and P2 dash, because they are relatively seen the same as with this transformed object, but calculated with the ray P dash on this original object. And now we can just apply the matrix M again, and then we get P1 is M P1 dash. In fact, we don't even have to apply that, because when we calculate the intersection points here, we get P1 is, let's call it P1 dash is the ray P dash with a specific parameter P1 dash. So this is the parametric equation of an array that we get when we calculate the intersection. We get a parameter t, and for that, putting that parameter into the array equation gives us the intersection point. So let's call that parameter p1 dash. And if we put that parameter p1 dash now into this here, then of course we get p1 of t1 dash, p1 p1 is p of t of p1 dash. So you see here, that's the key difference here. We have the p dash here, whereas here we have the p. So here we have the original ray, and here we have the transformed ray, and then intersected with the original document. If we put the same parameter in, we can easily calculate this intersection point. So we don't even have to calculate this intersection point here, and we don't have to do the transformation here, but we can just calculate the intersection point here. So you see that this works actually quite well, and that of course is much easier to calculate the intersection with a circle than with this transformed ellipse. But there are two common mistakes that are often made here, or two pitfalls that you have. I tell you the first one, and then I ask you, then you have to tell me the second one. The first one is actually related to what I just wrote down. If you look at this this equation here, when we want to calculate this point here, like very often when we do graphics and we have vectors where the direction only matters, like in the direction vector of the ray, then so the ray is defined as, we have a support vector E, and then we have a direction vector D, and that gives us then our ray. So the ray equation is P of t equals this position on the line plus t times the direction vector. So you can think about this as like really E gives you a spot on the line, and then you take have a direction, and then you have the parameter t that indicates how far you are on the line. So by increasing t, you kind of walk further on the line, or if we shoot rays, then we look further at more distant positions by varying this parameter t. And very often in graphics we just normalize vectors, because if you have unit vectors, the calculation often becomes easier. For example, when you do light calculations and stuff, especially because of the scalar product, because if you have unit vectors, then the scalar product becomes just the cosine, and you don't have to multiply it with the length of the vector, which is why often people sometimes, if they have a direction vector, they just normalize it automatically and don't even think about it. But if you do that in this case, of course you end up with a mistake in the end, because you see here that this position P1 or P1 dash of course depends on this t times d, so it also depends on the length of d. So if you normalize d in both cases, this, what I wrote down here, these two things here, don't work anymore. So this is one of the pitfalls that you have to be careful about. And that's already said that. And any idea what the other problem might be, or where you have to be careful? What happens? We had this before. I think it was even in the first practical already. When you do transformations. So what we do here is we shoot a ray to get the intersection point, and then we calculate the lighting. And how do we do that? With the normal vector, exactly. And you remember what the problem is with the normal vector when we do transformations? Exactly. We cannot use the same matrix. We have to use a different one, because the normal transformation, I already said that, the normal transformation, the transformation of normal vectors do not behave in the same way as the transformation of the objects. So we have to use a different matrix here. So if this is, if we calculate, for example, here, that's an ellipse, so it's, let's say we have here the circle, and we calculate the normal vector here, because it's easier to calculate, of course, the normal vector on a circle than to calculate it on a rotated ellipse. But if we then go back here, for p, we just multiply it with m to get the point p, but to get the normal vector, we have to multiply it with the inverse, the transpose of the inverse. So yeah, perfect, you were right. Good, yeah. So this is another thing you have to one of the two things you have to take care of. Good, so you saw now how we can really very easily create more complex models by this technique. Another thing that is often used in ray tracing is so-called constructive solid geometry, another thing that is used to create more complex models. If you think about it, in games you often just use triangles, because with triangle you can model everything, and triangles are very fast and they are supported by hardware, so you can do it quite quickly. But of course, so for example, you could, if you want to model something like a ball, or in 2D have a circle, or in 3D it would be like a ball, then you can say, okay, I just draw simple single triangles, put them next to each other, and if I take enough of them, then of course these corners here become so small and so smooth at the edge that it will actually look like a real round shape and not like single triangles. But and that is of course done in games, of course, when you program them, or when you program on the graphics hardware, because graphics hardware supports triangles. But if we do it with ray tracing, there is no point in modeling a circle with triangles if we can just represent it with a very simple circle equation. So, and because in ray tracing speed is a different issue than with interactive games. So for ray tracing, we would use the circle equation. But if we want to create like this ball or half a circle, of course we would only want to have this part here. So what we could do is, for example, we could say, let's define this part by a line in 2D or a plane in 3D. And then if we shoot a ray here, we get these two intersection points with the circle. And then we can just say, well, we have this line here, and the ball is only at the bottom of the line, so we just check on which side of the line the intersection points are. And if there are, for example, if there is one intersection point here, and and one here, then we know, of course, this is above the line, so it doesn't intersect with the ball, but this one intersects with the ball. But we also have to consider that this here, this here is another intersection point that we get. And this is basically the idea of constructive solid geometry. We create more complex models by concatenating simpler shapes. And for example, we could say we create a ball by taking a circle and then cutting off half of it by considering that everything that is on top of the ball as a different space, or that is on top of a line. Or we could do it, and that's what's actually done, we could take a circle and then we just take a rectangular or a square object, put it on top, and then we say we just look at the bottom of this. So we basically take this top objects and cut the intersection of both of them off, and then we have just this ball. And it turns out that when we do it like that, the calculation of the rays are quite easy. And so the constructive solid geometry is basically based on set theory. So we see, we look at objects as sets of points, and then we create more complex objects or different objects by making set operations on those points. So for example, you have here a circle and a square. Now you can make a union, and then you have this, whatever that looks like, a different shape, by combining and saying this new object contains all the points that are contained by the circle and all the points that are contained by the square. You could also make a difference or an exclusion by saying, for example, I take the square but remove all the points that are from the circle. Then you get something like this. Or you can take the circle and say I remove all the parts from the square, and then you get something like this. And if you turn that around, you have exactly the ball that I was talking about. So this is exactly the example I had in the previous image. Or you can take, of course, the intersection of the two objects, which in this case also gives you a ball, but a ball with a different shape or different size. Good. So this is the basic idea about how to create the objects. And the question now is how can we create easily ray intersections? And the trick here is that for the ray intersections, we move from looking at intersection points to looking at intersection intervals. So we basically look at the objects as if they are solid objects, and we look at all the points that are then touched by the ray if the ray would go through this solid object. So normally if we have an intersection with a circle, we are only interested in the intersection points, because when we're looking at it from the outside we don't see what's happening inside, so we don't care about this. We only care about the intersection points, of course. But now we're looking at this as a solid object, so we look at here the whole area in between. So we look at the interval and all the points in the interval between those two intersection points. And if we do that, and then the trick is that we can apply the set operations that we apply on the objects in the same way on the intervals, and that gives us then the correct intersections for this transformed object that we have. So let's look at an example here. This is the point where I would really like to have different colors here. So let's do it like this. We have the intersection with a circle that starts here and ends here. So we look at the interval. I'm not drawing it right now because then otherwise I cannot distinguish it with the other intersection. But this is the intersection interval. Starts at this position and goes until here, from here to here. Now if we calculate the intersection with S, with the square of the ray, we get a shorter interval that is here. Now if we combine these with the same set operation that we apply to the objects, for example, if we make the difference for the object, we get this like Pac-Man shaped figure. If we apply that to the sets, that we take this interval C and make the difference S, so we remove the parts that are part of the sphere and leave the parts in that are part of the circle, we get exactly these two intervals intersecting with this newly created object. And our intersection points are just the borders of the intervals. So you see, and that works also for all other kinds of set operations, because the trick is really here that we're not looking at the intersection point, but we're looking at the whole intervals. And of course it's kind of, if you think about it, clear why this works, because if we create an object by cutting off parts of it, then we are cutting off exactly the same parts of the intervals that intersect with the ray with it as well. So, or if we combine it, we combine the intervals with the same parts from the object that intersect with the rays. So it's kind of obvious that in the end we get the right intervals, and then the intersection points are just the borders of the intervals. Good. I basically said that. So we have now two ways of creating more complex models, and we saw how we can easily calculate the intersection points with them. But of course, if we have a lot of models in our scene and want to calculate the intersection points, then this takes a lot of time, which is why we're talking about faster ray tracing techniques now. And of course, I already said at the beginning that ray tracing is very slow. So we're interested in optimizing it, making it faster. And it is very slow because for each ray, we have to check all the objects. So we have a runtime that depends on the number of objects. So you can imagine if you have a very large scene, this becomes very slow. And also we want to add recursion, so we can't want to follow the rays and recursively follow them to get a better lighting and visualization and shading. So this is very slow, and the slowest part is really the intersection test, where we check rays, how do rays intersect with objects, or which objects do they intersect with. There are actually studies about estimating that that really prove that this is the bottleneck in ray tracing. So if we want to make ray tracing faster, this is where we have to start optimizing. And to do this, we're looking into several so-called spatial data structures, which is data structures to store information in a space in a very efficient way that allows us to do these checks very easily. And this is, of course, the motivation why we're looking into this today is ray tracing, but it is also used for culling. You remember we had the situation for culling that we said, for example, if this is our view frustum, then we see that these two objects are not in the view frustum, so we don't need to draw them, whereas these two objects here are, we have to clip them, do some clipping, and this one is inside the view frustum, so we draw it. So we also have a situation where we basically, in this case, not shoot a ray, but we have a direction or a plane, and then we want to know which objects are hit by it and which objects are not hit by it, are outside of it or to one side of it, so we can remove them. So this is also important for culling, and it is also important for collision detection, and this is the major relation or most important part, I think, from the ray tracing lecture that is, or from ray tracing techniques that is also important for game development if you program on the hardware, which is the collision detection. So it basically means if you, for example, if you select an object with your mouse on a PC in a game, in a 3D game, then you basically have the same situation. You have X and Y coordinates of your mouse, so you have a two-dimensional point on your screen, and you click on an object, and that object is in a three-dimensional scene, so you want to know which object are you hitting when you click on a specific point in the 3D scene. So this is basically the same problem as if you say I'm shooting a ray through that object in a certain direction, through that pixel in a certain direction, and want to know which pixel the ray hits or which pixel I'm clicking at, which object I'm clicking at when I'm clicking at this particular pixel. So this is the major relation to gaming, but we're looking at it from ray tracing today. Ray tracing perspective today, and there are two or the approaches for these spatial data structures can be categorized in two different categories, and let's start with the first one, which is the object partitioning scheme, because it's something that we kind of already we didn't discuss that, but it should be familiar with you because we were talking about bounding boxes before in relation to rasterization of triangles. So you know how a bounding box is created, and the idea of using bounding boxes for ray tracing is obvious. If you have a complex object and we make a bounding box around it, we can first check if it intersects with the bounding box. If the ray doesn't intersect with the bounding box, then it's obviously that the ray doesn't also doesn't intersect with the object that is inside of the bounding box, so we don't have to make a check with a very complex object. We can replace that with a pre-check with a more simpler object. At the price, of course, if it intersects with the bounding box, we have to do another check with the actual object to get the actual intersection points. But we say if we have a lot of objects, we usually save a lot of time with it because we don't have to check every single object with it, or we can replace the complex checks with a simpler check. So for example, in this case, we have here 3 simple checks that show us it doesn't intersect with the bounding box, so we don't have to do the complex check with this object. We can just remove them, and here we see they intersect with the bounding box, but here we see then we have to do a check with the object, which in this case leads to the object doesn't intersect, but here we see it does intersect. So we see we still made one unnecessary check, but at least we saved these 3 unnecessary complex checks. Good, so bounding boxes, I hope you remember it. If not, I can write it down again. So bounding boxes can be described as all points that are in the interval or in the box that is starting at the points x min, x max, cross y min, y max. So the x and y are from the vertices of the object. So we look, for example, at this object here, and then we see here this is the minimum x value of all vertices. This is the max x value, and this here is the max y value, and this is the min y value of all the vertices. So we see here that obviously if we take those values here and look at this square here, all the points in this square, then we have the bounding box, which is the smallest box around the smallest axis parallel box around an object that contains the whole object. Good, and now we have to do, now the question is how do we calculate the intersection points with this bounding box, and the answer is we don't care because we don't need the intersection points, we just need to know if it intersects at all. And that answer is easier to answer than calculating the actual intersection points because we can think about this in a way that we just look at the intersection of the ray, which is defined by, like I said previously, a support vector plus t times the direction vector. So we have here our support vector, which is at our I position conveniently. We learned last time why we choose it that way. And then we have a direction vector, d, pointing in the looking direction or the shooting direction of the ray. And then we look at the bounding box by looking at the borders of the bounding box or looking at them as lines or planes, lines in 2D, planes in 3D. So for example, this is the plane x equals x min. So normally if we calculate the intersection between a line and a ray in parametric equations, we set them equal to each other, but in this case we have a ray, let's call it xe, ye for the support vector, plus t times the direction vector, let's call it xd, yd. And that should be the same as this here. So we see we only have an x value here and not a y value in this equation because the y value doesn't matter for everywhere y value, just the x value we have every y value on the y-axis and the x value always stays the same, which is why we can set the whole thing equal to each other, but we can just take the first line here, which is the x value. So the intersection point must fulfill this equation here, equals x min, because the intersection point is of course also on that line. And if we transform that, so that is of course a specific t value, this value t for x min, then we get t for x min equals x min minus xe divided by xd. So this is just this equation which t brought on one side. So we have the t value, and we could now calculate this intersection point. And we can do the same for the others. So this is x max, so this is this one here. And this one is y min and y max, so this is here and here. And this is the one that I just calculated, so you see it's a little bit different, but it's different parameters, of course, but the same approach how we calculated it. But be careful, this only works if x and d are positive. If they're negative, the formula becomes a little bit different, but the concept, the basic idea is the same. And that way we could calculate the intersection points with the bounding box, but we don't need that because, as I said, we are only interested in the question if it does intersect at all or if it doesn't intersect. So what we do is we specify a test condition and this is what we're doing here is we're looking at the intervals x min till x max, that is this interval here, so all the values within here. Y min and y max is this here, and then we compare them with each other by this condition here. So the idea of this is basically the same as with constructive solid theory. If you look at the bounding box as a combination, as an intersection of a stripe like this, goes on here, and a stripe like this. So if this is stripe sy, this is stripe sx, then this, of course, is the intersection of sx as y. So we can do, if we do array check, we can check this interval here, which is this one, and compare it with this one here, or calculate the intersection here. And we don't have to calculate the intersection, we just need to check if these conditions are fulfilled. And we can see that quite easily if we think about it. If you have these two stripes here, for the left one, we say tx min is larger than ty max. So ty max is somewhere here. This is y max. So ty max must be somewhere here. Tx min must be somewhere here. So if Tx min is larger than Ty max, it must be somewhere here. And since it's the minimum value of the bounding box, it must point somewhere up here. Ty max is the maximum value, so it must be somewhere here, and it must point downwards, and it is smaller than T min, so it must be on this side here. Oops. So we see it points downwards, is on this side, it points upward, is on this side, so the interval starts here and goes up, this interval starts here and goes down, so the intersection of the intervals is certainly empty. And the same we can see here. If we do it here, we can argue in the same way, and then we'll see that this must be an interval that is somewhere starting here and going up, and this is an interval, the end of the interval that ends somewhere here and goes down. So we see again that the intersection is empty, so we don't have to calculate the intersection points, we just need to check this condition, and then we know the bounding box intersects with the ray or not, and then we can do our check. Yeah, but we have to be careful with these two cases. Like I said, the calculation changes a little bit when this is negative. I'm not doing this now because it's just basically looking at the images and see how the values change. I'll leave this as an exercise. If you're not sure, or if you cannot figure it out or want to verify your solution, you can look at it in the book. In the book they listed all the conditions. And also another case that is special that we have to take care of, if we have horizontal or vertical rays, then we get here in this calculation a division by 0, which of course is not a good thing to have, so we also have to do some special treatment here. But these are just special cases that we need to take care of when we do an implementation. But they don't change the basic concept, which is why I'm going to skip it now. Good, so this works quite well with bounding boxes, but of course there is no reason why we should restrict ourselves to bounding boxes. And if you remember what we talked about when we talked about volume culling, we just said we take a volume that combines certain objects in like a clever way, and we actually didn't even take bounding boxes, but we took spheres, because the spheres were easy to calculate the intersection with the volume. But we didn't say that this volume has to contain just one object, or that it has to be the smallest volume containing that object. And the same way we can argue here why we can that we say the bounding boxes don't have to have just one object, they can have multiple objects, which could make the intersection test easier. So for example, if we have something like this here, we see that we can remove those two, so we don't have to check two bounding boxes, but we just check one bounding box. It doesn't intersect, so we remove it. These two intersect, so we do another check. So we here check the three bounding boxes. These do not intersect. This one intersects, so we check the object. And this does also intersect, so we have to check the object here, but this doesn't intersect, so we can remove it. And if we represent those hierarchies in a tree structure, that we say the top is the largest bounding box, that contains certain other bounding boxes, which in turn contain other bounding boxes, then we can do the check with the first one that intersects. So we go to all the sons of this root, then we check with all them, with all the nodes here. This one doesn't intersect, so we can cut the tree off. We don't have to do the checks below. These two intersect, so we have to move forward down the tree. And then we see here that these two don't intersect, so we can cut the part off here. but we part of the tree here, so we don't have to do this intersection test, but we do this one, and we see it intersects. And we also can cut off this part because this bounding box doesn't intersect, but we check this one and we see it intersects. So by representing this as a tree structure, we can also easily and very nicely implement this and do the tests quite nice and well. Yeah, these are just some general comments on how to create these trees. Of course, it is not straightforward how to do this, and that is of course the difficult problem with this. If I give an example here on the slides usually, and of course I take a simple example, but in practice it is of course not always straightforward how we do this, and sometimes the creation of this hierarchy takes more time than the time we actually save with the intersection test. So there is, as with a lot of simplifications where we do additional stuff to make certain things simpler, there is always the trade-off on how much time does it take us to create these different representations. Good. Yeah, so you can imagine that there are a lot of like heuristics and approaches to group objects efficiently and effectively into bounding boxes. And also there is this other way around that we say we can argue why a bounding box doesn't, or a box doesn't necessarily have to be a bounding box, so it doesn't necessarily have to contain one element, but it could also be that we take several boxes that contain certain elements, like in this case, because you see here, if you have an object like this, or think about the example we had with the rasterization of the triangles, where I drew a triangle like this and then argued why a bounding box is not such a good way to save, because we need to rasterize all these empty pixels here, or check for the rasterization all these empty pixels. Same with ray tracing. We will shoot a lot of rays here just to get intersection tests with the bounding box, but not with the triangle, which are called false positives, which means that we have a positive test with the bounding box, but a negative test with the actual object contained in it. So the first positive test was actually false because we do not have an intersection, but it was positive for the bounding box. And of course, these cost a lot of time, so we want to remove them, reduce them, which is why there are a lot of other approaches. But yeah, of course, like I said, there is this trade-off, because you can think about it. The closer the bounding box matches the actual shape of the object, the less false positives you get, which is good, but the closer it matches the actual objects, the more you come to doing a test with the actual object. So of course that makes the intersection test and the creation of this hierarchy or these bounding boxes more expensive. Good. So these are the object partitioning scheme, because in this case we take the objects and partition them. And then there is another approach, which is the space partitioning scheme. But yeah, we're in perfect time now for a break.